So our goals today are pretty much the same as they have been. So basically we're going to continue applying Newton's laws. You'll find that this is basically the heavy weight of your next exam. It's applying Newton's laws in various situations, so that's why we're doing it every lecture. But now we're going to start to think about kinetic and static friction, which you've seen, you've begun to read about. And then we're going to introduce the drag force, and we'll talk more about friction and drag and how we think about them over the next day or two. Okay? So one good thing I would say about friction is that we have a pretty good intuition for it. Right? We're used to thinking about it in a lot of different aspects. So as far as gaining an intuition for this one, it's actually pretty straightforward, but there's some subtleties to it. But before we do, I want to do a review question from last time, because we're going to see this come back upon us today and next time. So let me launch this one. This is the same question we had before, same as yesterday. And the question is this. You have an object, a cart in this case, with wheels on a ramp, and there's a barrier. And the question is, the cart's weight is W, so what is the magnitude of the contact force acting on the cart due to the barrier? Right, so this was basically a vector decomposition problem. So take about 30 seconds to a minute and see if you can recall or draw in front of you this same situation we had last time. I'm going to draw it again on the board, but for a little bit later. Okay, so 3 or 4 more seconds. Okay, I'm going to stop. Okay, so I have 78% of you said A, that it's the sine of theta. So the force of barrier on cart is the sine of theta. Okay, so let's hold that answer for now, but then we'll move on to the other half of this problem. So again, just coming from last time. So the first answer we got, majority said A. What is the magnitude of the contact force acting on the cart due to the ramp? So this is what we would sometimes call, what would we call this force? The force acting on the cart due to the ramp. A normal force, right? We call this force barrier on the cart. Could we not also call that a normal force? Right? It's perpendicular to the contact surface. So in some sense, these are both normal forces, so that's why we're going to stick to this notation of ramp on cart or barrier on cart, because it identifies exactly those things. So again, take about 30 seconds to a minute. This is going to be, oops, I delivered the wrong one. Let me do that again. Just answer this one. The first one we said sine of theta. This one, the same choices. So either recall or have it in front of you drawn. Very simple. While you do that, it's up here. Okay, so about 20 more seconds. Okay, this is good. I'm actually content that you're getting this right. So 2 or 3 more seconds. Okay, I'm going to stop it. So get your response in. There's a handful left. Okay, this is a perfect response, right? Basically what I see is 90% said B. So they said that it was the cosine of theta. The last time it was 78% said that it was A. I suspect now people might go back and change their answer. But what did we do? All we had to do in this problem was break down the forces acting on the cart and find their components by applying Newton's second law. We went through this last time. We're going to go through it again today in a slightly different situation. Okay? So the answer is, in fact, A for the first one and B for the second. Okay? But we're going to see this again explicitly. We're going to be talking about friction and drag. So let me just introduce the topic, and then I want to show you how we can think about it. Here's the thing to remember about friction. So if I have motion in a system, the friction opposes that motion. So if I assign the direction of motion, friction always acts opposite that direction. Does that make sense with your intuition? Right? If you're sledding down a hill of snow and suddenly there's a patch of grass, what's going to happen? You're going to accelerate to slow down. So your acceleration is opposite your direction of motion, so you go to a stop. Okay? So friction opposes motion except in the case of the force of propulsion, which we'll talk about later. We won't talk about it here. The static frictional force is directed opposite to the applied force, and its magnitude matches the applied force. Okay? And we'll see this in a second. Up to a maximum value of mu Sn, where n is the normal force. So this is our basic introduction. Let me show you a few demonstrations here. I'm going to ask volunteers in a minute, but first one, really simple. Imagine I take the same situation that we drew with a cart on a ramp, but now I'm going to take a block, a wooden block, and I'm going to place it on this somewhat smooth surface. Okay? When I start to lift up, I'm going to lift up this side. I'm increasing this angle theta. You see that? At some point I can lift this up, and it looks just like the ramp on the cart on the ramp. Okay? Now, what do you expect is going to happen? If I lift this thing up, say 5 degrees, what's going to happen to the block? Is it going to slide or not? Let's see. I'll lift it about 5 degrees. What happened to the block? Nothing. Right? Let's lift it up, say 10 degrees. Nothing. Let's keep increasing it, then finally you see it starts to slide. Okay? So what's going on here? When I do this, we would say that this system is in equilibrium, right? There's no acceleration. The sum of all forces on this object are 0. But now when I apply a small angle, so let me do this again, just 5 degrees. I'll do it this way. Just watch. Is this system in equilibrium? Is there an acceleration? No. There's a sum of forces has to be 0. There's no acceleration. You see that this looks just like the problem we drew, except there's one thing missing in this problem, which is what? The barrier. Okay? So what's taking the role of the barrier in this problem? It's the force of friction. There's a force that looks just like this previous problem of the barrier on cart. What's taking the place in this problem is that there's a new force called friction that is basically acting in the same way. You could draw all the same components and see how this force behaves. Okay? Now, let's ask another question. If I have this slippery surface and I have a block on top, there's kind of a magic angle, right? So what's happening? I see no acceleration, no acceleration, no acceleration, and then I get to about here, here, here. This is good. It's working better than us. Okay, so about that. What do you estimate that angle to be?
45.
A little less than 45, probably 35 or so. So there was a critical angle at which, what happened to the block? It was static until it got to some angle, and then what happened? It accelerated. Okay? Do you see now the difference? Do you think that friction went away when it started moving? No. There's two types of friction. So friction is a bit of a strange force that we're going to talk about today. It has some empirical behavior that we know from experiment. And the behavior is exactly what you saw. When I lifted that ramp, the block stayed stuck. There was a force acting on it, but it was still in equilibrium. But as soon as I got strong enough, it began to accelerate, but there was still friction. There was what we call dynamic friction. So you see that now in this definition that I just gave you, and we'll come back to this problem in a minute, we have to now be careful the distinction between static friction and what we'll call dynamic friction or moving friction. Okay? And this is what the second part is. Once an object starts to move, static friction is gone, right? It's replaced with this thing called kinetic or dynamic friction. Okay? This is the friction that you feel as you slide down this ramp. Right? There's still friction, it's just a different kind of class. The kinetic frictional force is directed opposite to the object's velocity. Right? So which direction was this object going down the ramp? It was down and to the right. Which direction was the friction force of kinetic friction? Up and to the left. It's always acting opposite my velocity. It's acting to slow me down. Okay? The kinetic frictional force is directed opposite the velocity, and its magnitude is equal to mu kn. These two constants, this is called the coefficient of static friction, it's just a number. And this is called the coefficient of kinetic friction. Again, just a number, but it's proportional to the normal force, which is generally, and in almost all cases, less than the magnitude of the maximum static frictional force. Okay? So let's see if we can understand this. Before we do any math or anything else, let's see if we can understand this again. Can I have like 4 volunteers? Yeah? Yeah? Yeah, okay, that's 4. So come on down. Stand here for a second. You don't know what you got yourself into. That's okay.
This is how we done.
Okay. Here's a table on the floor. It has 4 legs. First of all, what are your names? Sarah? Jade? Nathan? James. Okay, turn around that way. Talk to them. Okay, good. So this is them. You just said their names quietly, which you'll learn as we go. Here's what I want any one of them to do. Who is the oldest? When's your birthday? Your Wait, who's the youngest? You're youngest? Okay, you'll be the first pusher. Okay, now try this. Show us what you can do. Just very, very gradually push this table. Now watch what he does. There's a table on the floor, and he starts to push. Go, push. Okay, stop. You see how easy it was? That was easy. He's a very strong young lad. Now slide it back. Slide it back. What happened at the beginning? Now do it again. Push very, very lightly. Just push lightly. Do you see that under really light pushes, he's too strong, even lighter. Try to get there. What he's doing is he's just barely applying a force. There's a force of his hand on that table. What does Newton's third law tell us? There's an equal and opposite force of table on his hand. Okay? Now he starts to push hard enough that it begins to slide. Okay? That's what we'll call kinetic friction. Now bring it back. Here's what we're going to do. This table has some, to him at least, negligible mass. Right? This was easy. So I'm going to ask Nathan, I remember that one because that's easy. I'm going to ask him to sit on the table right about in the middle. Okay? Lift all the way up onto the table. Legs up in the air. Yeah, there you go, like a slide. Okay, wait, pause. Don't push yet. What did I just do? I increased the mass. I have now an object that is pushing down on the table. What happens from Newton's third law to the force of the floor on that table? It increases by some proportional amount to his mass. So what just happened? The normal force got much, much bigger. What do you expect is going to happen for the pusher now? It's going to become much harder. Go ahead, push. But he's strong. Okay, he builds up his force. Keep it around. There you go. Okay, good. Wait, do it again, do it again.
I'm thinking sliding sucks.
He needs better shoes.
I do. I should take them off.
There you go. Okay, now, stop. You're going to hurt yourself out. You're going to have more to do. Okay, there were 2 things that I saw right there that were actually perfect examples of what we often see. Did you see how when it started moving, it didn't slide very nicely? It did this thing, what we call stick slip. It goes, right? It was basically dragging across the floor. Now, this is a perfect example of friction. That is the competition between what we will call static and kinetic friction. We'll talk about more details in a second. But the other thing you notice, go ahead and pull him back. Maybe your shoes are better this way. Yeah, so much easier. Okay. Keep going. Go all the way over to the middle. Okay, now, that leg went. Okay, easy does it. This table might blow in a second. Here's what happened. When he pushed on that table, right? He pushed on the table. Did it require more force when he was on it or less force to get it started? More. Much, much more. So there was this effort of him pushing on the table. What does that mean about the force of the table on him? Did it get bigger? Right? If he pushed more, it got bigger. It's still in equilibrium. It didn't start moving. Then once it started moving, what happened?
It was easier.
It was easier. Okay? So the force he had to apply suddenly dropped. Okay, let's try this one. Yeah, this one's good. Okay, move that one. Just pull that table out of the way. You can get off. So all 3 of you sit on this one.
Wow.
Try it.
Do like dumb.
No, not dumb. Just oh yeah, you okay, this is another one. Okay, he's gonna pull it. Wait, don't do it yet. Now, what do you think is going to happen to the force required to pull this table? So the force that he applies on the table, is it going to be bigger or smaller than what we saw before? Right? So now he's tricking us because he's going to pull it. So what's the table doing to him? There's an equal and opposite force of the table pulling back on him. That force, even though it's not going to move, he's pull on it a little bit, just not to move it yet. Pull on it. That's good. Right there, stop. Do you see that he has a force applied to the table? There's an equal and opposite force of the table pulling. No, stay there. There's an equal and opposite force pulling on him. Now, pull a little bit harder, but not quite enough to get it moving. Pull harder. Just lean back a little bit. There you go. Yeah, there you go. Now he's pulling more. The table's pulling more. What happens is eventually it'll start moving. Now move it. Go for it. Pull. Do you see how hard it is? Now wait, stop. You're going to hurt yourself. Now, take one person off. So you hop off. Try it again. Okay, stop. Take one person off. Try it again. Okay. So what just happened? Why did it become easier? Why did it become easier as we remove those people? It's less mass, and so what force became less? The normal force. Do you see that this force, he was pulling that way. Which direction is the normal force? Up. Do you see that it matters of the magnitude of the normal force, but not the direction, right? It's always going to be pointing up. It gets bigger and bigger and bigger and bigger, and it becomes harder and harder for him to pull. Okay? So give them a round of applause. We'll have them back next time. Okay, now this gives us some new intuition because we're going to start to try to understand this problem. So static friction is this force, this kind of new force that we're introducing that kept it from slipping. It was the thing that required to be overcome to get it moving. It was that time that he couldn't get it pushed. He couldn't move it. Okay? Now, it acts in response to the applied force. This is the part that's really counterintuitive. Remember we said, as he pulled harder, but it wasn't moving, the table was actually pulling harder on him. And harder and harder and harder and harder until finally it begins to move. So this static friction is basically going to respond to the applied force. Its direction is opposite to the applied force, and its magnitude matches the applied force. So static friction is a bit weird because it always tries to match the applied force. It gets bigger and bigger and bigger until finally it becomes dynamic. Okay? Now, eventually, that applied force exceeds some limit. And what happens when you exceed that static friction limit? What happened to the table? Yeah. It starts sliding. Okay? Now, what was the other observation that he made? Was it easier or harder to keep it sliding once it was moving? It becomes easier, right? So now the force he applied was less, and it was able to continue moving. So eventually this applied force exceeds a limit, and then the object begins to move. This is exactly what we saw. Now the last thing we'll say before we move on, and we'll do this more carefully in a minute, you said, all of you agreed, that as you added people, you increased the normal force. As you took those people away, you decreased the normal force. So somehow this force has to depend on that normal force, or the mass of those people. So let's think about microscopically what's actually happening. This is much more complicated, but we're going to just basically dump all of the details into this kind of simple frictional force. But really what happens is when you're pushing that object, there's a force of your hands on the object. We said that there's an equal and opposite force of the object on your hands, and those two forces oppose each other and grow until you begin to move. Okay? Now microscopically what it looks like under here is these things aren't perfectly smooth. Right? Friction comes from these kind of atomic scale, sometimes larger scale, micro scale, features in the bottom of these surfaces, or the interaction between these surfaces. Okay? And what happens is there's all sort of physics. There's a whole bunch of detailed physics, which I'm not going to get into, that kind of describes why this happens. Okay? But it happens, it turns out, this idea of stick-slip motion. Remember he pushed the smaller table, and it did this thing where it kind of shimmied across the floor? This is super, super common at the molecular scale in biology. Okay? So when you start studying the details of molecular motors and molecular biology, you'll see this stick-slip friction is one of the only ways we can really begin to understand it. So here's what it looked like. Let's imagine we draw for this situation here the free body diagram of the object, right? I've circled the object to make it clear, this refrigerator. So if I draw it as a dot, I would say that there's the force of this person pushing it, so the force of person on the object. There's an equal and opposite static friction force that's the equal and opposite unless it's moving, right? It's in equilibrium, so it has to be equal and opposite. There's the weight of the object, which is pulling down, and this equal and opposite normal force, which basically is equal to, in magnitude, m times g, the effective weight. So here's what happened, and this is the way we're going to kind of pictorially understand what we've already said. When you start to push, you apply a small force, the box doesn't move. At the next instant, when you push a little bit harder, you have to draw a new free body diagram because your push force is now bigger, but this friction force just reacts perfectly to counteract your push. So when you have static friction, it's like the thing is glued to the ground and it has to be overcome with your push force. If you do it again, you see that it continues to increase. So just a quick question, and we'll see this in a few minutes. If I plotted, if I drew a graph of the frictional force that's being basically in this free body diagram as a function of the force you apply, how do they relate? On a graph of frictional force versus applied force, what would you see? Can you imagine? If I increase my force, I increase the frictional force. I see people doing it. It would be a line, right? As I increase my force, the frictional force increases. It's just in the opposite direction. Now what happens? Suddenly, that motion starts to take over. He pushed with enough or pulled with enough force that suddenly this thing started moving. Okay? This is when we have to enter a new part of the problem. So if you're solving problems like this, you have to recognize that suddenly there's a new piece of the problem. Right? I push as hard as I can, now there's a new piece. I can show you back in this example of the wooden block. If I was solving this in some problem, I would say that there's the initial situation, which is I increase this thing, it's in static equilibrium. It's in static equilibrium. It's in static equilibrium. Then there's dynamics, right? So now the object accelerates. Do you see it's a lot like the rocket problem where we had to split this into kind of the launch phase and then the free fall phase? This is the way these problems will often look, is you have to first address the static frictional phase and then this kinetic friction. So once the object starts to slide, the static friction is replaced with what we'll call the force of kinetic friction. Now, if that object, right here, this example of the block sliding down, it's going down to the right, which direction is this force going to be pulling? Up and to the left. It's always going to oppose the velocity. It's constant, typically. This is kind of empirical, but it's generally a constant force, and it's directed opposite to the velocity. So we said that the static force basically increases. The harder I push, the harder the static frictional force pushes. But this one, once I'm going, it's a constant force that's being applied to the object. And experiments show that kinetic friction is less. Generally, it almost has to be less to match our observation than the maximum possible value of static friction. Once that object started moving, he said, it's much easier to move. I have to apply much less force to keep the object going. Okay? So we know that this kinetic frictional force is always going to be less than the maximum value of static force. Okay? So now we can think of this, going back to this kind of refrigerator example. Who's ever moved a refrigerator? Raise your hand. Oh, good, wow. When you push a refrigerator, do you just push it right on the side? What do you do? Tell me what you do. I see people. Well, there's a locking. Okay, good. So you lock it. But there's something even better to do. So next time you push a refrigerator around, who's ever pushed a refrigerator and gotten down really low and pushed up on the refrigerator? Okay? So if you're moving heavy objects, you will find that rather than pushing straight into them, you get low and you push up. Who's ever done this at the SRC, this big sled, right? These kind of, yeah, okay, good. It's the same rules. I see people, there's this big sled you just add plates to, put as many plates as you want. And I see people standing really tall and pushing this thing down and trying to run across the room. If you watch people that do it with form, they get really, really low and they push forward and up. Okay? Now, why is that going to be? Let's think about it. So here's this refrigerator, and you have a pushing force, and there's going to be this movement phase once it starts moving. Here's what the free body diagram looks like. Okay? You should have an intuition for this at this point, right? Once I break that movement, once I get this refrigerator moving, the force of my push is now larger than this constant kinetic frictional force. It has to be. Why do I know that my push force has to be larger than the pulling force, the frictional force? It accelerates, right? That's when the refrigerator begins to move. Now, there's a funny piece, though. Let's say I'm moving this table. I'll forget it later. I'm moving this table, but I'm at a constant speed, right? So I get this thing moving, and now I'm at a constant speed across the floor. Is this system in equilibrium? I see some yeses. Why is that system in equilibrium? Because I have a constant velocity. There's a balance of forces. My push force exactly equals the force of kinetic friction if I'm moving at that exact constant speed. Okay, that's a special case. So kinetic friction opposes the direction of motion. It is typically a constant value, right? It basically goes from this force that increases the more I push, which is the static component, and then it turns into a constant force that just fights the direction of velocity. Does that make sense? Let's see if we can put this into kind of the language of mathematics. So here's the next question. So here's the same basic situation, right? I apply a force. A horizontal force is applied to a block on a horizontal surface with friction. The magnitude F is gradually increased. So just like we said, I start to push harder and harder and harder. And it starts at 0 until the block starts sliding. This thing starts to move. And the question is, the force F then continues to increase. Which graph best shows the magnitude? Now be careful here. This is the magnitude of the friction force. And it's magnitude, so we're not worried about sign. The magnitude of the friction force acting on the block as a function of this applied force F. So I increase my force. How does the friction force respond? Take a minute. I have some responses already. It's already delivered, so take a minute. I think I have the right one. Yeah. So just think about what you saw when these folks were down here pushing on this table.
As soon as it starts sliding. You don't need it. Oh, you see it before. Okay, I didn't see that. I didn't realize it.
Okay, about 15 more seconds. So I have about 100 responses, so there's about 30 or so more, 34 or 40 more.
Oh no, I'm just kidding. It's a math question. I just think no.
Okay, 5 more seconds. I have a lot, most of them in. Okay, 3, 2, 1, good. Okay, here's what I got. So C was the dominant answer. It was about 70-some percent. 74% said C. Does anybody want to volunteer? Why did you say C? Why? Shh.
So you increase static friction and S max, and then it levels off at a constant kinetic.
Right. So she said you basically increase static friction until you reach a maximum value. It starts moving and then it levels off. It's a constant force. We basically said this in words and through examples several times. If I look at this kinetic friction is a constant directed opposite the velocity. When we studied this picture, we said that as I increase the push, there's a linear increase in the force of friction. So the harder I push, the larger the friction, the static frictional force. So if I put that into a graph and just stare at the mathematics, it's answer C, and you might see it a little bit more precisely like this. Okay? So basically, you see exactly what we plotted. And you can now put what she just said in kind of math. So she said that I increase my pushing force, and the static frictional force increases until it reaches some maximum value. What happens at this maximum value? What happens very suddenly? boom, the object started moving. Okay? Let's look at it again with this block. What is my experimental parameter in this problem? What am I tuning in this problem? The angle. Okay? And we're going to come to why this is related to the force in just a minute. You already know the answer. I tune my angle, I increase the angle, I increase the angle, I increase the angle. There is a static frictional force holding it in place. At some point, I overcome, give it a nudge, that static frictional force, and it becomes kinetic. Okay? So this maximum value is that angle at which it's just about to start sliding. Does that make sense in this ramp problem? We'll work through it carefully. It reaches that maximum, and suddenly there's this constant sliding force, right? This dynamic or kinetic friction force. So if I draw this, it looks exactly like answer C, which is basically the force. The frictional force increases as a function of the applied force and then levels off. And you can tell a lot from a graph like this. We still haven't even looked at the form of these forces. But when we find out in a second, we'll see that the frictional force is proportional to what force in the problem? You all knew this when we did this example. It's proportional to the normal force, right? If I had more people on that table, I had a much, much larger normal force. My frictional forces were much larger, okay? So you can actually get that information from these types of graphs. So let's see if we understand it. This is what I was alluding to a few minutes ago. See if we can explain this and challenge ourselves to really understand the answers. A refrigerator on a horizontal surface, so again, you're pushing a big heavy refrigerator, with friction is pushed by the same amount of force, F1, with different angles. Okay, there's A, B, C are the three situations. But the refrigerator doesn't move. So immediately, what kind of friction are we talking about? Static, right? It didn't move. Kinetic friction is when it's sliding. It's not sliding. In which case is the friction force on the refrigerator the greatest? Which case is it the greatest frictional force? So talk to your partners next to you, talk to your neighbors, see if you can answer this. I think I launched the right one. Yeah, good.
Because I remember him saying that. Because, okay, the first one he was saying if you put it straight on, it's going to heavy, put upward, and then it's going to.
Okay, so take about 30 more seconds. Try to convince each other that you understand the answer and that you can explain it.
Yeah.
Okay, so take about 5 more seconds. I've got almost all of them. Okay, I'm going to stop. Okay, good. Here was the question. Which case is the friction force on the refrigerator the greatest? Okay, and the answer that everybody gave, or a lot of people gave, 80-some%, 83%, they said C, that it's this case in which I'm pushing down. Now, why is that so? Does anybody understand? Why is that the one that gives you the largest frictional force in a static friction case? Anybody? Yeah. Did you hear what he said? He asked a question, but now say it as a statement. Okay, good. Now, hold your shoulders back, really confidently, and say it again. Good. Okay. What he said with confidence was that we increase the normal force. What happens? Here was my force that you guys chose. It's down and to the right. Okay. If I look at the components of this force, I have a component that is pointed down, and I have a component that is pointed to the right. Which of these components will basically increase the normal force? The downward component. If there's a downward component, there's an increase of the normal force of the floor on the refrigerator that counteracts that force. So if I point down, I increase the normal force. And why does the friction care about normal force? Because we said it's proportional to the normal force. Just like we added people to that table, we increased the normal force. What you're doing here is increasing the normal force by pushing down. Now this goes back to the question I asked before. If you have to move a refrigerator, what's the best way to move a refrigerator? Well, put it on a dollar or hire somebody if you easier than the dollar one, right? Give somebody your credit card. No, the answer is you basically push up. Why would you push up? Because it decreases the normal force. There is then a component that is pushed up and the normal force gets reduced. Okay? What happens if, this is just hypothetical, what happens if you were super strong and you pushed up really hard on that refrigerator? Yeah, it would go airborne. What happens to the normal force when something leaves the floor? It goes to 0. We'll come back to that problem next week because it's a really fun one. It's the way roller coasters work. Okay, so let me add one more. So we have static and kinetic, which we now have some intuition for. The last one you're going to see kind of in the homework, and we'll work through it a little bit, is what we call rolling friction. So this one, we will have a little bit of challenge. There's a homework problem that will probably show up. This one is a bit tricky. So the rolling one has to do with the contact of the tire with the road and how the forces interact at that interface. Because it's circular motion, analyzing this one requires a little bit of care, and we'll do that next time. Okay? But what happens is when you drive your car, the wheel flattens where it touches the surface, giving a contact area rather than just a point of contact. Does anybody in here drag race? My dad used to drag race. When I grew up basically at drag race events until I was like 7 or 8 years old. Has anybody seen a drag racing tire? What does a drag racing tire look like? They're about this wide, right? If you ever see a funny car, they're about this wide. They're circular in this direction, but they're very wide. And do they have big treads or not? No. What do they look like? They're perfectly smooth. Now, why would you want a soft, rubber, giant tire that's nearly perfectly smooth to make you go fast? More friction. Okay? Look, what this says, and this is why this one's tricky, and we're going to come back to this. The wheel flattens where it touches the surface, giving a contact area that is an entire contact area. It's not just kind of treads, knobby treads on your tire contacting it. You want this contact area to be perfectly in touch with the road. So when you see race car tires, they're very flat because they want lots of friction to the road. Why do we have big knobby tires when we're riding in the desert? Why do we have big knobby tires? Do you know? Well, it's not less friction. The problem is that sand moves. And you want a force that is perpendicular to the direction of the sand's movement. We'll come back to that problem next time. Okay? Tires are super complicated, but they're a lot of fun. Okay, so finally, after all of this discussion, here's the stuff that will really be useful to you for homework problems. We have a model for friction, and there's another type of friction which we'll handle next time, which is air friction or drag. Okay? But the three that we've talked about so far, this is how we're going to look at them mathematically. So static friction is always directed to prevent motion. When you have no motion, when you're still in equilibrium, it's static friction that's holding you there. And it has a magnitude that is less than or equal to this coefficient times the normal force. Do you remember we said it reaches a maximum value? That maximum value is the equal sign. At all other points until you reach that maximum, you're less than the maximum frictional force. Okay? Now, the kinetic friction force, is then once you start moving, which again you saw in the examples, you know what that means, and it's directed opposite to the object's velocity. It's typically constant, and that value is going to be some coefficient, so some number that depends on materials, etc., and the normal force. Okay? So again, if I put 10 people on this desk, and he was able to get it sliding, it would still require a lot of force to keep it sliding. It depends on that normal force. And then the last one is the rolling friction, and the magnitude is a lot like the kinetic friction. It's directed opposite to the object's velocity, and it has its own coefficient that depends on the surface of the tire, the shape of the tire, but again, on the normal force. Right? So if you want to go really fast, you want lots of contact area, you want a very high frictional coefficient. Okay? Now let me go back before we finish, before we introduce drag. Let me come back to this problem. Okay? We said, in terms of forces, we said that there's kind of a static force that increases and then reaches a maximum value. Let me frame this problem. I want to introduce this and we'll come back to this next time. Let me draw this problem just like you saw at the beginning of the class. Here's my mass M on a ramp. Does this look like a cart on the ramp problem? Almost exactly. Okay? If I have weight pushing down, I have a normal force perpendicular to the surface. What is the other force? When this angle increases, if I'm still in equilibrium, which direction and what is the force that's holding this thing in place? We now know it really well. Static friction. Okay? You see that this looks identical to the situation of that barrier holding the cart on the ramp. Okay? At least in terms of the forces. Now, if I look at this, I can take components, and we did this many times now. This is weight times cos theta. This is weight times the sine of theta. Okay, so this was the problem we asked at the beginning of class. If I know this thing, I can now start to understand this frictional force in a very different way. So what I can say is, I increase this angle, and I keep increasing and increasing and increasing. There's a sudden angle, there's this kind of magic angle where this thing starts to slide. Okay? So I can look at this and I can say my force of static friction is going to be equal to weight times the sine of theta. Right? So these are equal and opposite. We're in static equilibrium. So up until that point where I start sliding, the magnitude is going to be the weight times the sine of theta. Right? This is just basically Newton's second law. But what happens is there's a maximum angle, right? At some point, this whole picture breaks down and it starts accelerating. So I can label this that there's some maximum value of the static frictional force that is fixed to this magic angle. Once I get to that angle, I've reached the maximum frictional force, and then it starts to accelerate. Do you see that? This is basically just a combination of what we've done in the past, and now we have this friction. Now there's another piece of information, which is that the normal force is equal to weight times cosine theta. And that's equal to mass times g times the cosine of theta. Right? This is just doing the sum of forces is equal to 0 in the perpendicular direction. Again, we did this last time. Right? We've worked through this before. Now I can write down an expression from this that tells me about this particular system and the static coefficient of friction. Let me erase this. So let's say that at that special angle, again, let's say that this is the exact picture. I go to this angle of something like 30 degrees. I have a maximum angle, and I have a force that is a normal force at that angle associated with it. All I'm going to do, we know that weight is equal to mg, right? But from this equation, we can rearrange to show that mg is equal to the magnitude of the normal force over the cosine of that angle. Right? This is just algebra. And what I'm going to write down over here is the force of static friction at that maximum point. And I'm going to simplify. I see that this is equal to mg. I'm going to replace that with n divided by cosine theta max. And I have a sine theta max, so it looks like this. N over cosine of theta max times the sine of theta. Can I simplify this one step further? How do I simplify it? Tangent, right? Sine over cosine is tangent. What's the form? What's our generic form of the static frictional force? It has some coefficient, just some, it's about the materials, it's a number times the normal force. Do you see that in this particular problem, I now have written down this static friction coefficient. If I have a material You can intuit this. If I have a material that's stickier, it has higher friction, what do I have to do to that angle to get it to start sliding? I have to, if it's really, really frictional, it's sticky, and I keep lifting and lifting and lifting and lifting, it's going to stay right in place until I get a much, much bigger angle. If this thing was polished, and we'll do this example next time, what would happen? As soon as I start to lift, it would start sliding. So do you see that the material, the interface, what's going on microscopically, is all buried in the angle at which it starts to slide? Right? So in this problem of a ramp and this sliding object, I can write down an explicit form of this coefficient of static friction. We're going to come back and clear this more next time. We're going to see some of these examples.